Hello, ladies and gentlemen, and welcome back. Root Beer here, and I'm going to be finishing off the 2018 Open paper. We're on to our last question, question C4. This is typically the hardest question on the contest paper. Hopefully you've given it a try before coming and watching the video or reading the online solutions. Let's dive in and take a look, shall we? Given a positive integer n, Matt writes n in decimal on the blackboard without writing any of the leading zeros, which is odd because you don't really write leading zeros anytime you write a number, but okay. Every minute he takes two consecutive digits, erases them, and replaces them with the last digit of their product. So before we go any further, quick story. I remember this question. I don't remember how to do it because I never actually finished it. But I remember when this particular Open came out, and usually the harder questions, somebody will hand me a copy and say, hey, can you do them really quickly because we want to teach them to our group of whatevers. So, I usually get handed, so they'll say, oh, I can't do C3 or in C4. Usually it's C4. Sometimes they can't do C3. Anyways, I remember getting this one, and I misread the instructions, the erase two consecutive digits and replace them with the last digit, which I believe makes the question a lot easier. I thought it was take two digits and replace them with their product, period. Which I think if you've read the question, we'll read the question together, but makes it a lot harder. I still think that a lot of what they're asking can be done. I think C part, I'm assuming, is the really big... Yeah, for a finite set. So C part, I think, can still be done if you misread it like this. I had to write a computer program just to even try and find a pattern. And I think if you just take enough sevens in a row, C part can be done. I can't remember. I never actually finished it, but it seemed ridiculously hard for a high school contest. And then somebody pointed out to me, oh, by the way, it's the last digit. Because I kept going on about, oh my gosh, this is so hard. This is crazy. Why would they put this out? So I guess the lesson here is very carefully read the questions. But if somebody wants to try the harder version, like try and do C part to this question, but replace the two consecutive digits with their product rather than their last digit, and let me know how that goes, because I would love to hear about that down in the comments below. Anyway, we can continue reading the question. As I say, I never actually finished this one, because it was somebody pointed out to me my error in reading this well after interest in the Open had died down. And I didn't want to continue doing it because I didn't want to spoil my attempt at it when I did it for you guys. Anyways, any leading zeros created this way are also erased. So if you have something like 1, 0, 1, and I multiply the 1 and the 0, it gets replaced with the 0. But we ignore that, so we would just get 1. Same thing with, say, a 2 and a 5 and a 1. Those guys would be 10, but we don't write the 10. We write the last digit, because we read questions carefully. But that would be 0, 1, and we don't write the 0. That sort of a thing. Okay. He repeats this process for as long as he likes. We call it the positive integer m obtainable from n if, when you start with n, there's a finite sequence of moves Matt can make to produce the number m. For example, 10 is obtainable from 2, 5, 1, 0, 2, 3. You multiply the 2 and 3 together, you get the 6. You multiply the 2 and the 5 together to get 0, but we ignore the 0. It's the leading 0, and so we're left with 106. Multiply the 0 and the 6 together to get this 0. All right. A part. Show that 2018 is obtainable from 2, 5, 6, 7. There's 4 7s. So let's actually start writing this down. Then I saw a 9 there. 8, 9, 9. Okay. And we want to sort of go all the way down and get 2018 out of all of this. Well, I have a 2 here, so I suppose if I can just turn the rest of this into 0, 1, 8, that would be nice. So it starts with a 2, so that's fine. It does not end with an 8. So this 8 here, could I get rid of the 2 9s? And I think there's sort of 2 ways we could do that. We could group the 8 and the 9 together. That would be 72, but we would just write the 2. And then with the 9, then group those together, and 2 times 9 is 18, so you just put the 8. Of course, that's not the only way to do it. we could multiply the two 9s together to get a 1, 81, and have an 8, and then group those together to get the 8, too. So really, what we're saying is these last 3 can combine to become the 8. But let's show them what we're doing. It doesn't really matter which way. I said the 72 one first, didn't I? But it's more about the product of those last 3 ends in an 8. And this is something that's kind of important. We are working with remainders when you divide by 10. We are working with just units digits. This is also called working modulo 10, if you're familiar with modular arithmetic. But that might play a bigger role in the B and C parts as the question gets more complicated. Usually for the first question, if it's a well-written contest, which the Open tends to be, same with Waterloo contests tend to be well-written, when they introduce a brand new concept like this, the first question is usually a gimme, did you pay attention and understand the instructions? So I've got a 2 and an 8. I just need to turn this middle bit into a 0 and a 1. But look at these 4 7s here. So 7 times 7 is 49, but it becomes a 9. And if we were to do 7 times 9, you'd get a 3, because that'd be 63. Or you could say these 3 7s together are 343, because I know my cubes. 7 cubed is 343. It ends in a 3 just as well. But we can say 3, 7 here, and 8. And then we can put the 7 and the 3 together and get 21. So now I've got my 1. Now how to get a 0? Well, the 5 and the 6, I mean, they're what's left over. I guess I'd have to combine them. Now, it might be that I haven't done this right, but I think I have. So, yeah, 5 and 6 end in the 0, so we get the 2018. Okay. And we've shown exactly what we're doing each time. So our process is clear. I don't think we need to explain this at all to anyone. And no words. Just show them what your work is and say, there it is. You got it. Okay, so B part. B part. Find 2 positive integers. Actually, I'm going to read B and C part together. But find 2 positive integers A and B for which there is no third number C, so that A and B are obtainable from C. So it's sort of some sort of contradiction between the A and the B. Okay. C part, and the reason I'm reading these 2 together, and this is a sort of a general rule if you're looking at C4 on the Open, or 10 on the Euclid, or B3 on the Canadian Senior Paper, what they tend to do for last questions, and I like this trend, I like that math contests are doing this, is for their last hard question, they will introduce a brand new concept. In this case, this sort of process that Matt is doing. Okay? And sort of the challenge is, it's a hard question, difficult concept. How well can you cope with this in the time allotted? Can you develop the theory quick enough and rigorously enough? And I like this. If you look at, say, Euclid contests from the 70s, quite often towards the end there'd just be a really hard geometry question. Well, some people have more geometry knowledge than others. Whereas this, I mean, anyone can tell you they're 10 times tables and just look at the last digits. Anyone can approach this. But because of this trend that they just hand you a giant concept, it's usually a good idea to read the whole question, all the parts at once, so that, usually A is, did you read the instructions? B is, can you take this a step further? Can you do this calculation? Can you notice a simple pattern? C, D are, can you take these patterns to the extreme? Can you do a really complicated version of whatever it is we're asking? Can you generalize the examples you've seen so far? And so it's a good idea to read the whole thing so that those B, C parts can give you direction for the D's and E's, the later parts, so you know what patterns to maybe try to be looking for as you go along. So that's why I recommend reading the whole thing together. So there's B. And now C, let S be a finite set of positive integers, none of which contain the digit 5. So this is giving me a little, I would say probably hint towards B, that the digit 5 might be hard to work with. Okay, they're specifically saying, for what you're about to do in C, ignore the digit 5. Prove that there exists a positive integer n for which all elements of S are obtainable from n. Yeah, so this is really, really giving us a giant hint to C, because if I chose A and B to be, A could be 246 and B could be 81117, what C part is saying is because there's no 5s in here, I guarantee you'll be able to find some N, or for B part C, that does this. So you sort of have to have a 5. Now we could just play, if we did just read B, we could play around with it as much as we want, but looking at the C sort of gives you a bit of a hint. Play around with 5s, get something that's got a 5 in it, make 51 or something. Find some way to get rid of those 5s. Or find some problem when it comes to those 5s, I guess. Now, for both B and C, I think it might be a good idea if we take a look at the 10 times tables, but with just the last digit. So 0, 1, 2, 3. So we'll just take any of the possible digits, because all we do is take 2 digits, combine them. And it's a useful thing, not even necessarily to have written out during your solution, but just to have off to the side as a quick reference, on a sheet of paper over here while I'm doing the rest of my work, so I can quickly say, okay, they combine to be this, and those two, they combine to be this. So it's just a good thing to get, but we can also try and notice some patterns here. So zeros are nice because zeros just eat everything else. It's going to take us a little while to fill this whole thing in. 1 doesn't ever change anything. So I would say from the point of view of this process, Matt's process, 1s don't really matter, I think. 4, 6, 8, 2, and 5 is 10, but that ends in a 0. 2, 4, 6, 8. So you notice 2 sort of has a nice little repeating pattern. In fact, only 1, 3, 7, and 9 should have all the digits in them, because those are the only ones that have a GCD of 1 with 10. This 9 counts down, actually. It's a 5. 4, 3, 2, 1. And 6, 5, 4, 3, 2. 8. 2 times 8, 6. And 4, 2. So it's counting the other way around. I am quickly running out of space for the 7 times tables, so let's rewrite the 8 times tables. So these sevens are going to be a bit jumbled up. 7 times 2 ends in a 4, then we get a 1. It's like we go down by 3 each time, so this should be an 8, a 5, a 2, a 9, a 6, a 3. There we go. And same the other way. 8, 1. Three, 9, 2. Oh, it's going to be the reverse of the 8 times tables, isn't it? 2, 5, 8. 4 and 4 is 6. 5 and 5 is 25. 6 and 6, 6 there. Zeros. One thing I'm noticing is the 5s are, so the zeros sort of ate everything. The 5s are alternating 0, 5, 0, 5. So once I have a 5, either I'm going to eventually make a 0 or I'm going to make more 5s, depending on whether I multiply by an odd thing or an even thing. 6 and 4 is 4. We got a 4 there. Okay. So that finishes up the whole thing. Now, in terms of trying to make things two things that, let's say, don't have a common obtainable ancestor. 5, definitely big hint from C part, but what could go with 5? And it doesn't have to be 5 itself. I think having single digits might be a nice thing to shoot for. They're very basic, but maybe our A's and B's will have to be more complex. I don't know yet. But just looking back at this table, I like that when you multiply by 5, you're quite restricted to zeros and 5s. Are there other tables, or are other parts of the table that seem quite restricted? Not in the number on top, but more in the sort of the output. Red box around these. Because I like that multiplying by 5, sort of having this 5 here limits it to being zeros and 5s. But say the 7 times tables, or the 7 column, every number is represented. So having 7s around sort of gives you a bit more freedom. You might be able to get anywhere you want with some 7s. But if we look at the 6s or even the 4s, you know, as soon as you've got an even number, you're forced to get an even number. In fact, we can go the other way. In order to have a 5 in your answer, you must have started with a 5. I think we could probably justify that. In order to get an even number somewhere in your answer, you have to start with an even number. So it's not quite as strong. So, you know, to get a 4 in the end doesn't mean you had to start with a 4. You could have 22 will reduce to a 4 quite quickly. But you will need to have some even numbers, because if you just have odd numbers, well, I don't care how you combine those odd numbers, products of odd numbers are odd, and therefore their last digit is odd. That's the test to see whether or not you're an odd number. What's your last digit like? So I think knowing that, so if we were to pick, say, A is 4, B is 5, I think that would cause some problems, because if we think through this for a moment, in order to get that 5, you must have had a 5. Okay? You could have lots of 5s. You could have a bunch of even numbers. Some of those 5s and even numbers give you zeros, which then become leading zeros, cancel out. But you will have to have a 5 if you end up with a 5. I think that's sort of a rule. So if we want to get that 5, that means we must have had a 5. If we want to get a 4 in the end, it means we must have had an even number. And maybe having an even number and having a 5 in your number together doesn't work out, because look at what even numbers times 5s are. They're not 5s, they're zeros. So 4 will work, maybe 2, 8, 6, anything but 0 I think might be a good idea. So I've got a plan of attack. Let's see if we can work something out. Let's see if we can justify it. Okay? So the 4s and the 5s look good. Things like 7s, 3s, 1s, 9s, those columns seem to allow any number, and that's not quite nice. So I'm going to say off the top of my head, I claim A equals 4, B equals 5 will work. I think any non-zero single digit for A would work, but 4 is the one I mentioned first, I guess. Now, I don't have a direct proof of this. We are going to play around and see what we can justify. So notice, and this is where you could say, I've made the chart. Here it is in my notes really quickly. So notice the only way to get a 5 in the decimal notation after a step in the process is to have a 5 before the process is done. Is that clear? I think that basically 5s can't come out of thin air. You could probably even paraphrase that. You could put that in brackets. 5s don't come out of thin air. Neither do even numbers. So I could say similarly, looking at our chart, to get an even number, we must start with an even number in our digits. Okay? So, I don't know where these numbers are going to be exactly. What do we want to say? So the idea is, so if I just had a 4 and a 5, those would combine to be 0, and that's really it. There's nothing you can do there. If I spread them out, well, let's say, so I know I'm going to have a 5. I'll have some numbers in between. What's the next even number to the right or maybe to the left? I don't know what I'm going to need to do. So we'll make these all odd. And then there might be more numbers here and more numbers here. But I want there to be a problem. What shall we say? I'm going to say... consider two numbers D and E. And we'll say D looks like D1, D2, D3, D4, all the way up to Dn. And we'll say there's one step in the process, and this goes to E1, E2, EK, and then a 5. Okay? And we'll say this is one step. So if I do this step and I end in a 5, what could I have beforehand? And maybe I'll need a few of these digits here. So how could I get a 5 here? Well, either Dn is a 5, in which case, maybe we reduced somewhere else. Or if we're only doing one step, if we have a 5 here and this isn't a 5, it's got to be some other number. So let's say, or we combined Dn minus 1 Dn into a 5. So 1 must be 5. So if it's not Dn, it's got to be Dn minus 1 is a 5. And Dn is odd. So that's an observation. I don't quite know where it's going yet, but let's notice something else. Let's say, notice that if A1, A2, well, no, I might want to use those for my, no. Let's say X1, X2. So if this is a set of digits, and so what I want to say is sort of what I noticed with the 7s and the 899 is that if you take a chunk and you know they're going to reduce down to a single digit, it doesn't matter which way you do it. But of course, that's not the case, because if I've got evens and 5s, there might be some way to make a 0, and that would cut off, like if that turns into a leading 0, that can cut off a whole bunch of stuff. So if this is a set of digits that is none of them are even and none of them are 5, so odd digits that aren't 5. This might be helpful for C part too. So we'll say a set of digits that are odd and not 5. And if we reduce down to a single number, call it y, y is the units digit of x1 times x2 times xn. Since no leading digits can be 0, since that requires an even and a 5. Okay, in fact, we could go a step further. If x1, x2, xn goes down to y, and the xi's are even but not 0, or odd but not 5, then y is even and not 0. And I think the same is true if the xn's reduced down to y and the xi's are odd and at least 1 5, then y is equal to 5. So these are some nice general rules we can observe based on the multiplication table that I drew earlier. And the only way to make a 5 is with some 5s, and only odd numbers can lead to more 5s. The only way to make even numbers, well, you have to start with an even number, because if you multiply a bunch of odds, it'll still be odd. In fact, we should probably write that down. Y is odd here, and it's not going to be equal to 5. Okay, so we're putting a bunch of things together. So, what can we say here? So if we end up with a 5, we must have at least had a 5 here. That 5 might propagate back, and as we move further back, might move up a bit. But the only way to produce a 5 is to have a 5 and then an odd, or an odd and then a 5. So I think it's safe to say, let's let C be C1, C2, C. I'm not going to say N. Let's pick another one. Let's say R. Just so it's a completely different letter, because I might continue to accidentally use N as I have. All right, so this is the C I start with. Suppose C reduces down to 5. Then obviously C So in order to get a, well, I haven't covered all the cases here. So if there are no 5s, there's no way you could make it a 5. So obviously one of the C's has to be a 5. But it's the leading 0 stuff. That's the problem. Because otherwise, every number would just reduce down to the product of everything, and this wouldn't be a question anymore. We must have at least one CI equal to 5. There might be more. Now suppose C reduces, what did we say, 4. Right? So this was our B, this was our A. Then at least one CI is even. Can we say that even and let's say not 0? I think that's fairly safe to say. So, I would say by star, C1, C has got to be equal to, since we reduce down to 5, sort of only ever, the only way to make a 5 is with 5 and an odd, 5 followed by an odd, or an odd and then a 5. So this is equal to, let's say, call that one I, call this J. 5, and then a whole bunch of other ones, all the way up to CR. Each is odd. Let I be the largest index, with CI being 5. Okay, so they're odd, and now I can say they're non-zero. They're not 5 as well. Okay, so that's giving me a little bit of a handle on what such a C might look like. We want to show such a C is impossible. So that tells me J must be less than or equal to I minus 1. That is to say, C looks like C1, and then, I don't know, some E for even. I don't know what the even number is. And then there will be a 5. And then a whole bunch of odd things. Okay. So that's nice. In order to make a 5, you have to have that. But in fact, let's say let J be largest index where Cj is even and not equal to 0. So now I know whatever's in here is either 0 or odd. Okay. So that's nice. Now, in order to reduce down to single digits, this is why I chose 4 and 5 to be my targets. Other things might work, but this is why I chose 4 and 5 to be my targets. Basically, everything in C has to collapse. Either things will combine, become leading zeros and go away, or they will all reduce down to a single digit. And depending on the way we do that, depending on the way the zeros wipe things away, we might get a 4 and a 5, but I'm betting not. Okay? I'm hoping not, although because I've spent a fair bit of time on this, but if I'm wrong, I'll restart again. But, where to go from here, really? So to have C reduced down to 4, really any even number, I probably could have just picked, I don't know, a generic one. I could have just said it doesn't really matter. But let's say, okay, we're going down to 4. So I don't think I can have zeros in between these two. It has to be odds. Can we have 0 between E and 5? And I'm willing to say the answer is no. Because if you did, and a whole bunch of odd stuff there, how are you going to get rid of this 0? Eventually, So to get rid of this, since 4 has no zeros, it must combine with what's before it to give a leading 0. But then we'd be left with a bunch of odds and 5. So all odd, some of which equal 5. And that can't reduce down to 4. Well, let's just say it automatically goes to 5, which you might recall from basic math is not equal to 4. Okay, so you can't have a 0 in between there. Otherwise, you'll never reach 4, but does that even really matter? Because eventually this E has to combine with this 5. So if there are no zeros between E and 5, then I would say eventually, so E will combine with some of this to make another even number, call it F. And then the 5 will combine with some of this stuff to make a 5. But eventually those will combine to give a 0. Now there might still be some stuff over here. There might still be some red stuff over here, some other numbers that haven't combined with this 5. Basically, odds and some 5s will produce a 5. Even and some stuff will produce another even. And there could be another 5 in here, so this could even be 0. But the point is there's at least one 5, so you'll definitely get 0. And then be left with this red stuff, which is all odd. This is a leading 0, or will eventually get removed when it combines with stuff that might have even been beforehand. All that goes away, and then you're left with x1, x2, xn, all odd. And this reduces down to something that's odd, possibly 5, who knows, depending on where we've placed our 5s. So, I guess I don't want to write that out in full because that's going to be a lot of words, but let's say E combines with this, the purple bit beforehand, let's say the blue bit, the pink bit, this 5, let's see, the green bit and the red bit. So all odd, 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 not odd. There are no zeros in here. E will eventually, well, we don't really care what those are. They could be not odd, they could be, it doesn't matter. It does not matter at all what's before the E. So E will eventually combine with the 5 to make a 0, or be absorbed by another 0. I have no idea how Matt can do what Matt's going to do, but he can do lots of things. No, so why eventually? Because we're trying to reduce down to a single 4, and we've got so many numbers, we have to get rid of them. The only way to get rid of numbers is either to combine them or to merge them with zeros that become leading zeros and then they get on out of there anyway. So the e will have to combine with something, either with a 0 somewhere else, or eventually with that 5 that's sort of standing in its way. Right? If there wasn't the 5, if e were just the last digit and it happened to be even, then maybe everything before it would go away and you could somehow get down to a 4. But because of what we observed, the only ways to make a 5 in your last digit is to have it be combined with some odd stuff beforehand, or have it eventually sort of undo the process, keep going backwards, backwards, backwards. Eventually you'll see 5 and just a string of odd stuff. And we saw that. That's the only way to make a 5. So eventually we'll combine with the 5 to make a 0. And so cannot make a 4 as needed. Okay. I don't think that's my most elegantly worded argument, but I think the main beats are there. The emphasis that you would want to place, if you want to write this up better than I'm writing it up, is there must be an even number, and there must be a 5 further to the right of it, and odds afterwards. And so in order to get down to a 4, you have to use this even number to make a 4. In order to get down to a single digit, every number has to be used, possibly being thrown away as a leading 0, but eventually it has to be used. But because of that, the e will eventually collide with odd stuff times a 5, maybe this odd stuff with a 5, and will produce a 0. And a 0 will never lead you to a 4. Okay? There's a lot of variation here and different ways to express it, but that's the main idea. And I'd rather move on to C part. I think we've done enough pictures. I'd be interested to see how many pages their solution is for this. Are they quite rigorous, or are they just saying, here are some observations, obviously this must be true? I hope it's not the latter. Anyway, Waterloo sometimes gives out ridiculous... COMC, the open is not done by Waterloo, but I know Waterloo sometimes will give like a 5-page solution, which is fine, but, how are you expecting people to write 5 pages? Anyway, all right, let's talk about S, finite set positive integers, none of which contains the digit 5, because we've seen how 5 and even numbers don't mix well. Prove there exists a positive integer n for which all the elements of S are obtainable from n. Okay, so I don't know what my finite set S is going to look like, and this is the problem. But I do know it's finite, so there's only so many digits. So I would say the holy grail for this sort of a thing is to say, here's a string of digits, you can combine them however you want, and you can combine it in some way and turn it into what you want it to be as a digit. But obviously we've seen that can't exactly happen. For example, the only way to make a 0, say all they're saying is there are no 5s, so say they want a 0. The only way to make a 0 is to start with a 0 or have an even and a 5. Well, we probably want to avoid 5s if we can, but maybe we'll have to do that. But 0 seems to be a very particular thing. Whereas, we might start focusing on, can we make even digits? And yeah, you probably could. If you had enough 2s in a row, you can make any even number, because the powers of 2 go 2, 4, 8, 16, but that would just be a 6. So 4 2s together can, taken in groups, combine to make whatever you need. Although the problem is, if I have 4 2s, well, we sort of already observed that it doesn't matter how you combine this, you're going to end up with a 6. If I combine just parts of it, I can get the 8 that I might need. But I would need to find a way to get rid of this other 2, possibly with leading zeros. And that could run into a problem, because then we'd probably want to stick a 0 here, but if we've got other digits to work out, that 0 is not going away. So what we almost want is, I'd like a way to get single digits. I think that's a little too complicated right now. So we could focus on even digits, we could focus on odd digits. I'm not sure what the best thing to do would be. So if I have a whole bunch of 2s, I can make whatever even digit I want. If I have enough 2s, if I have 4 more 2s, I could, say, turn these 3 into an 8 and these 3 into an 8, and then try and get rid of these 2, or maybe use them in the next 4 2s. Then how would I get odd numbers? Well, I'd need to start sticking in something that gives me odd numbers. And 3 or 4 3s or 4 7s would do the trick, because, you know, as I already remarked, 7 times 7 is 9. I suppose we could write it like this. 7 and 7 goes to 9. 7, 7, 7 automatically, however you combine those in whatever order you want, will give you a 3. And 4 7s will give you a 1. Just like combining parts of this can get you whatever even digit you want. But if I were to say, all right, put enough 2s here to make whatever. So S is finite. S is finite. There's only going to be so many numbers in there. So there is a limit to how long those numbers are. There's also going to be a limit to how long a sequence of even numbers in a row could be in any of their decimal representations. So I'm only ever going to need so many groups of 4 2s. And then we could try to use sort of 7. Some 7s in front, but I feel like we're going to have 2s left over, and those are not exactly going to play nice with the 7s, if you see. Suppose we could go about the other way. We could have groups of 7s, and then enough groups of 7s for any string of odd numbers, and then have some 2s in front. Are the 7s going to cause us... If I've got too many 7s, is that going to cause a problem? So let me illustrate what I'm talking about as I try and ponder it. So given enough 2s, here's a group of 4, so given 8 2s, so 2 groups of 4 2s, I can make any 2 even numbers in a row. Take all of these, and they would combine to the 2, and then leave them alone for the rest of this, and then combine these 2 to make a 4, but then I'll have some 2s left over. Now what I'm thinking is, have enough 2s, then I have a whole bunch of 7s. Right? But now that I've used these 2s to make the 4, these 2s to make a 6, what am I going to do with these 2s? Suppose the next thing I want is a 3. I want to use these 3 7s. These 2s are now in my way. And if I start trying to combine them with the only way to get rid of them is to either combine them with the 4 or start combining them with the 7s. Is a pickle. If I add in more 7s, because 7 and 3 are both quite nice in that if I have enough of them, I can make whatever it is that I need to. So if I were to add on, say, a few more 7s, I wouldn't even need that many. Yeah, that should be enough. So reserve these 4 7s to make the 3 or whatever it is I need, and we'll deal with any extra leftover 7s there for a moment. But with enough 7s, I can say, this is a 4, make that into a 4, actually combine these into a 6, and then can I do, so 7 and 6 would be a 2, and then use another 7 and that 2 to be the 4 that I need. And then instead I could use these 7s and let these 7s carry forward. So, They would then combine with the sort of string of 2s, and you'd get sets of 4 2s. And it doesn't have to be 4 2s. It could be not 6s or 4s, but 8s would also work. 4 8s can produce any even number if we go back to the little 10 times table. And maybe I should take another look at that. So could this get me an odd number followed by any even numbers? Yes, but what if I want a string of odd numbers in a row? Because these 2s will have to go somewhere. I think the problem is odd trumps, or even trumps odd. So maybe instead I need to work at it with, groups of 7. Groups of 4 7s to make odd numbers that I want. And then to have a bunch of 2s here to make just about whatever even number I want. Yeah, so then I could make, let's say, 3. Because the thing that 7s can't do is make 5s, but that's okay. They said no 5s. So maybe I need 3, and then another 3, and then a 7. And then I'll have, so that's 3 digits, so I'm not going to do any more. And then I've got 5 7s left, and they would combine with the 2s to make even numbers. Although having 4 2s here, if I then wanted another odd number afterwards, so this is essentially the same as having a 6, so we don't really need that. We just have 1 2. And then, if these 7s would produce a 4, it goes with this 2. Maybe I don't want an 8 there. I suppose maybe we could borrow some 7s? Well, no, because maybe it's going to be all 1s, and I need all 4 7s. So maybe tack on a few 7s just for the heck of it. So, new idea. We will have groups of 4 7s. Enough so that you could make any string of odd numbers that appears in any of the things in S. And then we'll have another group of 4 that's a 2, a 7, a 7, a 7. I was about to say, does it have to be in that order? And yes, it does, because then if I've got too many 7s, they can just feed into the next one. And 3 7s is enough to do it, right? Because it would be 2, and then if you did another 7, it could be a 4. If you needed to use the next 7, it could be an 8. If you use the final 7, it could be a 6. So yeah, groups of 4 like that. And then keep going on with more 7s, and then an even. And that way, suppose I want 2 even numbers in a row, just combine all of this into an even number. And so these would be, in fact, these are 1s, so they can just be completely ignored and you'll get another even. Oh, that's even better. Suppose the same thing would work with 3s, because 4 3s ends in a 1 as well. So this is looking good. So as it stands right now, I can make any sequence of odds, and then evens, and odds, and then evens. I will, however, get sort of an excess of 7s populated with the occasional 2 at the front. but I can get odds and evens except zeros. But we might be able to use the zeros to get rid of the other numbers, the excess. Because I'm worried about, so we use the 2 and some of it's 7s, but then whatever 7s are left over get pushed into the next group of big 7s that are used to make odd numbers. But if you keep pushing, eventually this digit n has to stop, and you don't want to be stuck with a bunch of stuff at the front that you can't get rid of, and that's where the leading zeros can come in. Because 0 can just eat anything. Okay. I think we're ready to put this together. I need two things. Since S is finite, let, I don't know, P be the number of the maximum number of zeros. Well, I suppose we can just get away with number of zeros, but maximum number of the zeros appearing in any one number in S. Because S is a group of numbers. And let Q be the length of the longest string of consecutive odd digits in any member of S. Okay. So here's my plan. I'm going to have 4Q7s followed by a 7772 followed by 4Q7s No, do I want that? Do I need something else? Do I also need an R for the longest sequence that doesn't have a 0 in it? Yeah, I think so. So let's say let R equal longest string of non-zero digits. Okay. So now we're going to get what's the easiest way to write this out? Let's let I be 4Q7s. Let J be 77Q. Let K be JI, 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 R times. And I'm going to say let L be 0K, 0K, 0K. I think I'll need another K up front. It can't hurt to have more Ks, but we'll say that happens P many times. So this is where I can get those zeros if I need them. And then, oh, this is actually going to work out nicely. I think we're going to get to N. M will be KL. And I need a 0 in front, but I also need a leading thing, so I don't know, 1, 0, M. Okay. I think this will work. It might need a little bit of tweaking. But I claim n suffices. And now I have to explain why this works. So if we were to pick there's some S in S, that S looks like at most, what do we say, R non-zero digits, and then possibly a 0. Most R non-zero digits, 0. And then sort of, because we said R is the limit, so at most R digits, and then at most P zeros. So what I want to do is show that this can be achieved no matter what it looks like. Okay? Have we covered the even numbers properly? Yes, because at most I could have R even numbers in a row. Actually, I probably could have just defined R and let this be for R7, but it doesn't really matter. Okay. So, I claim I can produce any string of, well, let's say JI. So let's say from each I produce now. So there's going to be some. I know what I want in my head. It's difficult to write out, and I know the video is getting long. So from I, we can produce any string of Q odd numbers, Q or less, let's say. Odd numbers what haven't I used? Let's say K. Possibly with some extra 7s up front. These 7s, or let's say then, take a J followed by the extra 7s, and this can produce. Also, you might want to point out, 7 goes to a 7, 7, 7 goes to a 9, 7, 7, 7. I don't think we've actually written it down. I've articulated this idea to you guys while talking, but it should be pointed out that you should explain how that works. So this can produce any even number, say E, possibly with more 7s. Take those extra 7s, and add them to the next. It should probably be pointed out how the sevens can work. I can go to 4. That can those ones. I wrote this out earlier, but we'll just say 8, and then all of them together would be 6. And if you need to add those 7s on, that's fine as well. Anyway, take those extra 7s and add them on to the next I. We're working right to left. So in this way, we can make any string of, at most, are non-zero digits from, what did we call it? K, I think. From K. Okay. So I buy that. And then so once I've got that, so now we've got our non-zero digits from K. And so all those Ks can produce what they need. Oh, possibly with extra 7s. Use the zeros in, I think we called it L. Actually, I suppose we could just chop it off there and say, so I don't know where the last group of n things is. So we'll say there, we'll say n is like this. All right, and then so we got those zeros. So use the zeros in and to absorb the leading 7s once the non-zero strings in S are made. And then use the 1. Well, use the 0 after the leading 1. To absorb any extra zeros and Ks not needed. And this, S could be a very small thing, in which case we've got a lot of stuff that we don't need. Then use the 1. Well, so then what we've got, so then we have 1, 0, S after all this. And then so then combine the 1 and the 0 to leave me with S, depending on whatever S I need. So there we go. I'm not sure this is the simplest N, but this one worked for me. For example, I think there's a... I almost want to say there's too many 7s in I, but then no, because if so, I thought what I had while I did this was just alternate even, odd, and get 4 7s to make an odd, 3 7s and a 2 to make an even, but you can't get rid of those 2s. They have to go somewhere, and they keep making even numbers. So really, yeah, you do have to go stretch of odds, even, stretch of odds, even, and that stretch of odds could be 0 odds in a row. You could have a bunch of evens in a row. But it has to be done like that. So there we go. But that finishes off question C4. That was part C there. And we're all done our 2018 open paper. It's quite a long question, but well, Wasn't that bad, I don't think. Certainly a little easier than the first time I ever saw the question. Anyway, thank you guys so much for watching. If you're looking for more math contests, of course, you can just browse my channel. You'll find whatever suits your fancy there. Until the next time I see you, have a wonderful day.